Awesome. Let's get started. Welcome back, everyone. This is week 3, and we've sorted out the technical issues. Sorry about that. The ones that we had to face last week. We'll be talking about fine-tuning models today using fast.ai, and we'll have presentations from Wayde. He'll be talking on Blur, as well as please make an important note. He will say no, but you must call him the professor. Zach, so make sure you call him the professor. He'll say no, he doesn't know what to call himself. I'm telling you to do that. And after that, Arto will also present about his framework. So it's super exciting stuff, and I won't talk about this because I'll pretty sure butcher it. I'll keep an eye out for the questions. Keep them coming in the chat. And now over to Wayde. Please take it away.
Awesome. Can everybody see my screen?
Yes, I can.
Mouse moving. All right, awesome. All right, so welcome back. We're at week 3, and this is one I've been excited about because this is the fine-tuning week. So if you've been keeping up with the course content, essentially they're looking at ways with Hugging Face and also just with PyTorch and their Accelerate library, how to train transformers. But since we're doing things with the FastAI-ish bent, we're going to be looking at 3 approaches to training transformers with FastAI. So go ahead and go through this. So essentially today we're looking at section 3, and I'm going to go through the section 3 content really quick so we can get to the demos. Strongly encourage everybody to go back, look at the course, watch the videos, and be able to run the examples there. That will only help your learning. And again, our goal this week is in particular to understand how to fine-tune Hugging Face transformers with FastAI. And like I said, we'll be looking at 3 different approaches: AdaptNLP, Blur, and Fasthugs. Again, the resources, if you have any questions during the week, please post those to the Discord. And again, depending on where you're at, we got resources for learning FastAI, for actually working with Hugging Face with FastAI, or just general ML data science, in particular with the Chai Time Data Science podcast, and also Weights and Biases. And I think you'll see a little brief demo of Weights and Biases that I'm going to provide, and then Arto has a much more extensive, more razzle-dazzle demo to show you as well. So fine-tuning a pre-trained model. We looked at this mostly last week, but if you're looking for a data set, go to huggingface.co/datasets, and there's all kinds of ways to search and find something that is relevant to the domain that you're working with. And we also looked just, very simply that they have a nifty map function. If you need to pre-process data, you can batch this as well, so that instead of doing 1 example at a time, you can do 4 or 8 examples. And then there's typically some other work you have to do with removing columns that don't matter, renaming columns, and then formatting it, in our case, for PyTorch. And a nice thing, if you are using data sets and you want to quickly iterate through your training loop, you can create a subset by using the select method and passing a range. And so in this case, if you want to just kind of get going and make sure your training loop runs, instead of loading all 100,000 training examples, you could just load the first 100. And then we also talked about last week this idea of dynamic padding. So here it's like, essentially the idea is, instead of just batching to the max model length, you're going to batch to the longest length of a sequence in a batch. And this is recommended, mostly because it will make your models train faster, and you'll have less padding tokens. So you're probably going to get better results. The other thing they talk about in this week's section is using the trainer API. And this is essentially a high-level training evaluation loop that you don't have to code. And it can run on multiple GPUs, TPUs. There's lots of options. You can use things like mixed precision. And to control this, you basically create a training arguments, which is like essentially your config for how it's going to train. And you pass that to a trainer object, and it just does its thing. And so if you're looking to just a high level, just to use Hugging Face and train, this is a good option. but we can also use PyTorch. And so this should all look pretty familiar to most folks by now. And here we have our training loop where we're going through our data loader batch at a time, putting on the right device, passing all of our inputs through the model. And so remember, this is going to be your input IDs, your attention mask, maybe token type IDs, depending on the model you're using. And in this case, we're going to let Hugging Face calculate the loss itself. And that's going to be accessible right here using the loss property on the outputs object. Then we call backward, get our gradients, update our weights, move our scheduler one step, clear everything out, and so forth. So pretty standard stuff. And then on the other side over here, they have an example of using their metrics library. And so you can actually pass in a data set, get the metrics associated to it, and then loop through your evaluation data loader. And at every batch, add the predictions. And at the end, compute them and get your results. So if you go through the course, you'll see the trainer API example. You can run that in Colab. You can run the PyTorch example. And then they also have this library called Accelerate. And essentially, the shortcoming of the trainer API is that you lose control over the training loop, right? It does everything for you. The nice thing with PyTorch is that you can control everything. And so with Accelerate, you are essentially using that PyTorch loop that we just saw with some just minor changes. And all of a sudden, you can have distributed training. You can train on one or more GPUs or TPUs. And again, when you look at the documentation, you'll see examples of how to do so. You can run that in Colab. It's really cool. And this is something that I remember a while back, Jeremy Howard said that Sylvan was going to help work on in terms of integrating into fast.ai. I don't know where that is, but when it's there, definitely it's something that we're going to want to use. Any questions on any of that speed through of the course? It took me a lot longer to go through the course than that.
I think it made sense to me. So if it makes sense to me, I'm sure everyone would have understood.
All right, cool. Okay, so again, go through the course. You can see how to do this, how to fine tune with PyTorch and Accelerate and the trainer API. But how do we do this in a fast.ai world? And so we're going to look at three approaches. We're going to start with Blur, which I'll demo. Zach is going to demo his work with AdaptNLP. And then last but not least, Arto is going to demo Fasthugs. And he's got all kinds of like nifty stuff in his demo too. So I'm kind of jealous. And anyways, we'll get started. All right, so I'm not going to run through everything in real time. I've already ran through this for the sake of time. But we're going to look at fine tuning with the Blur library. And first, I wanted to state my design objectives, and they're fairly simple. So first is I wanted to make a fast.ai first library. So that means that when you look at Blur and you use it, it should be really familiar to you. If you know how to work with a CNN learner or with a learner to do image classification with the CNN, this should all look really familiar to you. And you can follow essentially the same steps to train a transformer. The other objective was to support core tasks out of the box with any transformer architecture. And so Blur supports causal and mass language modeling, sequence classification, token classification, extractive question and answering, summarization, and translation tasks using almost any transformer architecture out of the box. So very rarely will you have to implement your own callbacks or transforms to handle the particular inputs or outputs of any given transformer architecture. And if you look at the documentation, I don't test all the transformers, but you'll see tests for most of them. And then the other nice thing with this is that if you're running experiments and you want to play with different architectures and see how they work, literally you can just swap out the checkpoint and say, like, I'm using Roberta base, and then I'm going to use dberta. I'm going to try BERT base case. I'm going to try BERT base uncase, and you won't have to rewrite any code to make that happen. And then the last one is to keep things flexible and extendable. And this is something you'll see in common with all of the approaches, is that all of us are using fast.ai transforms and callbacks extensively to do a lot of the magic. And just like fast.ai, you can take blur as is, or you can customize any of those points. And as a side note, if you're doing fast.ai, highly recommend you spend some time understanding the callback system by looking at the callbacks, and you can kind of see how they work. That's really where, again, I would say most of the magic happens with fast.ai. So let's look at the code. So we're going to import a bunch of things. And in honor of our host, I'm going to actually do some really simple weights and bias stuff here, just to show you how easy it is to get going. And thanks to Morgan for walking through some of this with me. So in this example, we log into weights and biases. And the first thing we're going to do is essentially configure our model class and a checkpoint. And all of us are going to actually show you how to demo the MRPC data set. And I'm going to follow, for the most part, what you see in the course documentation. And I think Zach and Arto are as well. So you're really kind of saying a one-for-one, like from the transformers, from doing this in PyTorch and with the trainer, how to do this in fast.ai. So with kind of our model class and checkpoint configured, we move to actually getting our data. And we've showed this before, where we can actually load a data set. And once we have a data set, we need to, because we're working in fast.ai, is define a validation data set. And so here, I'm going to find the validation indexes, and then I'm going to concatenate the two data sets, because fast.ai likes to get, especially when you're using the data block API, everything in one source, your training and your validation data. From there, I calculate the number of labels we're working with. So remember that if you're working with something other than 2 labels, this is something you're going to want to pass into your configuration object. So it's good just to get it anyway. And then with Blur, with this information, we can go ahead and get our architecture. We can instantiate our configuration, tokenizer, and model object. With that, we can construct a data block like this. So we're going to use Blur's HF text block. And then for our targets, a category block, since we're doing a multi-classification problem. And again, the data block is essentially a blueprint for how to transform your raw data into numbers, something that can go through a model. And so here we're going to define our getX as sentence 1 and sentence 2, our target label, and then we're using the index splitter and the validation indexes we defined above to define what our validation set is. And then we can go ahead and call data loaders. We're going to pass in some other parameters for batch size and validation. And then again, just like fast.ai, we can go ahead and call show batch. We pass in the data loaders again. This looks kind of odd, but we're passing this in so I can get access to the tokenizer, the Hugging Face tokenizer, to control the output that you see here. Once we have that, we can train. And one cool thing with weights and biases to get things training, once you have your project and your run configured, which we did in the these quargs above, we could just call it init and get things going. And it actually has a nice little visual plugin here that runs in your notebook that actually updates in real time, so you can see how your run's going. And then we have a couple options for building a learner. So we can go this approach, which is doing everything by hand. But we also have a higher level learner that basically a class that derives from the fast.ai learner called a learner, pronounced learner, but it looks just like learner. I don't know if it would be better to call this BLURNER or what. So I just kept it like this for right now. But these are called learners. And it basically, a learner encapsulates all of this stuff right here. So depending on, it it basically just does all this out of the box. And then you could pass the same things you can to a FastAI learner. So you can pass other callbacks, you can pass metrics like we're doing here, and it returns a frozen learner, which means that all the parameters out of the box are frozen with the exception of your classification head. And so we can do that right here. And once we have that, we can start training this just like any FastAI application. So we can use the LR finder. And here I'm pulling back the minimum, the steepest part of the curve, where the valley is, where the slide is. And it's nice because it shows you all those things. And you can see that in the course, they use 5e-5, which I'm just going to use here. And if you kind of look at it, like usually you would start here or here and go back 10x, and it kind of gets you in that 5e-5 range, which is kind of interesting. And then to use weights and bias is just a callback that you use when you call fit. And once you have this, it will actually start logging to weights and biases, and then you can actually go to wanb.ai and actually look at all your training runs, which is really cool. Also, just as a side note, when you look at this notebook, I have little tips. So when you're looking at this and you're exploring ways to improve it, I have little tips about things you can look at. And so one is actually looking at papers. If you're using burp based on case, go to the burp paper and look at what they used and they had success with. That will give you a good idea of where to start. So we're going to train, and we actually get pretty good results here. We get about 0.9 on the F1 score, about 86% accuracy. And then we can also, just like FastAI, show results. We can run learn.validate, look at our validation information at the conclusion of everything. We can get our predictions with called a get preds. And then the wanb.finish basically says this run is done, and it closes things out for the next run. And then also, again, because we're using FastAI, we can do inference just like we normally do. We can export a learner called load learner, and then actually pass in a single or a list of examples or of text for it to do predictions on. And the big thing here is that it just has to be in the format that the data loader got its training and validation data. And so with the data, since we're using the datasets library, we're looking at list of dictionaries. So you pass in a dictionary or a list of dictionaries. And then batch interest is super easy. We can just, on the learner, access the testDL method from our data loaders. We're going to pass in a subset of our test data set and get predictions. So super easy if you're working with a test set that is either labeled or unlabeled after the conclusion of your training. And then lastly, we can also use the high-level API in Blur. So for each task, we have a high-level learner. And so here, I'm importing learner for sequence classification. And just to make this interesting, I'm actually going to use a data frame. It can actually do data frame or list of dictionaries out of the box. And with data sets, there's this nifty little .2 pandas to take a Hugging Face data set, convert it to a data frame. And once we have that, I'm defining another column called is valid, right? False for the train, true for the validation DF. And then I'm going to concatenate everything. And then because I am using a data frame with that is valid equals true or false, by default, the from data frame method will use a call splitter and split on that. So that's how we're going to get our validation and training set. And so you can see with using the high level learner is we essentially pass in our data source, our checkpoint, our text inputs and labels. We can pass in our data load, our data loaders quargs, and also pass in learner quargs too. And this is going to return a frozen learner, just like we saw above. So I'm going to unfreeze it and train it for 3 epochs at 5e-5. And again, the results are going to differ because it's probabilistic, and there's things are initialized a little bit differently, and the order of the batches might be a little bit different. But we get pretty close to the same results as we did above in this run. And then again, since a learner is just a learner, we can do show results, we can export, we can load, we can do predictions. It's got to be in the format that it was trained on. And then we could also do batch inference, just like we did above, this time on a test data frame. And that's basically Blur. That's how you would fine tune anything. This was sequence classification, but again, it would work for any of those core tasks that I mentioned above. And with that, is there any questions yet, Sonia?
Yeah, there was a question in the YouTube chat. So the question is, are there playlists? Yes, there are playlists. You can find them on the Weights and Biases YouTube channel. These videos are being put there. The other one, I think you've already answered it, but it might be worth diving into. If you could talk about the purpose of HF splitter that we're passing in the learner.
Yeah, so HF splitter is kind of a like most Hugging Face objects have a certain architecture. And so with HF splitter I essentially split the parameters into 3 groups. So the first one is kind of the initial parts of like the encoder. The second part is the second half of the encoder. So if you have like, let's say you have 12 encoder blocks, right? And we talked about this back in week 1, I think. The splitter will have the parameters in the first encoder block be in one layer group, the second in a second layer group, and then whatever your head is, like the classification head in this sense, that will be in a third group. So you can look at the source code and see how that works. Sometimes it's helpful to actually freeze everything but the head that hasn't been trained. A lot of times it's not, and it's just you'll get better results if you unfreeze everything. So that's what the splitter does. And you can also pass your own splitter. So there are folks who have not had success with the defaults in Blur, so they create their own splitting function to do that.
Awesome. No other questions.
All right. So with that, I'm going to stop my share. I'm going to hand things over to Zach to give us a look at AdaptNLP.
Oh,
Professor Zach.
That's
correct.
terrifying. All right. Hopefully we can all see this okay.
Yes.
Perfect. All right. So hi, everyone. My name is Zach Mueller, and I'm a machine learning engineer over at Novetta. And I actually got my start through the fast.ai framework. And so it's very precious and dear to me. And so I try and apply it in everywhere I can. And since I'm here, you can guess, I applied that to transformers. So today I'm going to be talking about AdaptNLP and fast.ai, finding and filling the gaps with the transformers framework. So what is AdaptNLP, first of all? Beginning in February of last year, Andrew Chang, a former employee at Novetta, saw a need for a simpler API when it came to doing inference with Hugging Face. At the time, the pipeline API wasn't quite flexible enough for what we needed, and we were hoping for something we could deploy quickly, and no matter what the situation, it just worked. This became a variety of easy modules, basically designed for quick inference with multiple models, multiple sentences, multiple queries, all at the same time, while keeping them all in memory and with strictly very easy to use interfaces, hence the easy names. As a company, Novetta kind of saw a benefit for making the library open source. And since then, it's had some community engagement and some interesting use with the library ever since. Below, I have linked to the documentation and the GitHub as well. Now, let's get on to what we care about, AdaptNLP and fast.ai. About 6 months ago, I was placed on the project, and shortly thereafter, I became the lead developer for it. And coming from a fast.ai background, I really wanted to try and integrate the fast.ai suite because I knew if we did it well, it could help us modularize our code and help us with the long-term goal of a centralized fine-tuning API. Let's dive a little bit more into what I mean by this. So it started out really simple. We were basically designed as an inference framework, as I sort of mentioned earlier. And so I wanted to start slow and rewrite all of that backend. And I accomplished this through the fast.ai callback system. As Wayde mentioned, it can be a powerful tool, as well as converting the library over from a standard Python library to notebook dev through another library called lib2nbdev. And then from there, basically, I started trying to build what I thought a good, intuitive, fine-tuning API would be that leverages fast.ai as best as it can while still making creative and intuitive decision choices for the user, so that if you just didn't want to think about anything and train a model, that is an option for you. Might not be 100% the best, but it's going to be close to the best. But now the question is, why use fast.ai? Why should I take the effort to integrate this framework into our existing project if we're already got our foundations in PyTorch? And that starts with callbacks. Now, as Wayde sort of mentioned earlier, understanding the callback system is, in my opinion, the single most important thing you could possibly learn about the fast.ai framework. Yes, you can learn the data block API and what have you, but if you want skills that will really help you leverage the fast.ai framework to its fullest extent, it is the callback system. And the reason for that is it gives you full access to the fast.ai training loop. People tend to get an idea of, because you're letting fast.ai's learner take control of everything, you have no freedom. You can't modify any step, and it's sort of, there's little roadblocks for you. And the reality of it is that's actually not true. It helps keep your code modularized and clean. It becomes easier to work with and refactor in the future. And in our example for AdaptNLP, it let us reduce our boilerplate code by about 80%. One instance is, say, I need to adjust how my inputs are gathered. So in fast.ai, normally this is just a batch of tensors, and we need to convert that to a dictionary for Hugging Face. So I just wrote these, when you really boil down to it, 8 lines of code as a callback that takes in the raw data loaders, sets it up as a dictionary, and I can go ahead and pass that to my model. And it's little things like this where once you write the foundations, everything else for the integration becomes seamless. Now, new to this sort of framework, before the callbacks was specifically to help with inference and mildly with training. Now we're going to talk about that fine tuning that I mentioned. So when I was writing this fine tuning framework, I wanted to take as much inspiration from fast.ai as I could without using fast.ai directly, because there's essentially 2 routes you can take: using only fast.ai for absolutely everything and wrapping around its framework, or understanding that fast.ai works with anything and just view it as a training framework. I chose the latter while trying to emulate their very intuitive data block API. So what this essentially translates to is a high-level API that anyone can approach without losing any flexibility, a mid-level API, and in my head, this is something that can take Hugging Face data sets and converts it into more or less raw Torch data loaders, and a low-level API where you just pass in a raw PyTorch data set and a raw and just data sets in general. So on the right here, we're going to go a little bit more detail into this in the demo, but this is an example of what I mean. It looks very similar to the tutorial that you guys followed throughout the course, but we just wrap everything in this task dataset class. And it looks very similar to, say, fast.ai data block or fast.ai data sets. And we build data loaders the exact same way by calling .data loaders. And so these were the key importances I saw when it came to a user perspective of someone trying to learn a new framework, when we assume that they already kind of know what fast.ai is, but they don't want to deal with the struggles of its data API. So next, onto that training API, because that's really where the real meat and potatoes sort of come from with the framework. Now, all of this is actively in development, like literally added a new thing last week. But essentially what I wanted the new fine-tuning API to be is more than just accept some data loaders and train. I wanted it to be able to work with FastAI's learner, but have two interfaces, a high level interface where the user only gets access to about 5 or 6 different functions that have specific names and specific meanings, or a low level interface where it can expose the FastAI learner and get access to the entire framework. And the goal of that is so that new users aren't confused by hundreds upon thousands of different little functions and attributes affiliated with the learner, while still being able to not lose any of the flexibility and anything that the original FastAI framework allowed for. And so an example below, I have something called a sequence classification tuner that looks kind of similar to a FastAI learner. We pass in some data loaders, a model name, the Hugging Face tokenizer, and set a number of classes. And then we call tune, which is sort of similar to FastAI's train. We'll look a little more in detail during the demo for that, which we'll do now. So we're just going to follow the MRPC dataset, which all the demos will be doing. And we're going to be installing FastAI here. Now, I'm not going to run through most of this, but I am going to show some explicit things. Specifically here, I'm installing the GitHub version of AdaptNLP because all of my code right now is on the dev branch until we have a next release. And then we also install my version of NBDev, and I'll show a little more on why that later. But for now, just know it's NBDev with a few little bits. You're going to notice that a lot of this code is going to look very similar to the Hugging Face tutorial. So we're going to load the raw data sets, and then we're going to import the task dataset class. We're going to need the name of our model we want to use, a tokenization function. Now, this tokenization function should take in a row, a tokenizer, and any keyword arguments for the tokenized function, or essentially when we call the tokenizer. You don't need to worry about tokenizer or the keyword arguments. All you care about is making sure that what is being passed to tokenize from this item matches what needs to be essentially performed. So here we tokenize both sentence 1 and sentence 2 together and join them together. So I'm going to write my toke function as doing exactly that. Next, let's look at what the task dataset API needs. So this is that little NBDev addition that I mentioned. We actually have function arguments documented for you for quick use. So we see it wants a trained dataset object, and this is the Hugging Face datasets, a validation dataset, tokenizer name, whether to tokenize it immediately, that tokenize function I mentioned earlier, keyword arguments for the tokenizer, as well as for the auto tokenizer itself, that constructor. Any columns we want to remove, just like how you would have remove calls in Hugging Face, as well as that tokenizer name. That's a little bug, but that's all right. Once we have our data sets, we'll go ahead and say we want to remove sentence 1, sentence 2, and index, just like we did in the tutorial. I set a max length to 64 just as an example of something you can do, as well as set padding to true. And with everything in place, we just pass it all in. So we pass in the raw data sets, train and validation, the model name, and all of our other arguments we had earlier. And finally, we need to build some data loaders because we right now have a perfectly built data set. We just need to send it off to the data loaders. So similar to how FastAI has .data loaders, we have .data loaders here as well. We pass in a batch size and a collate function. And for that collate function, we're going to pass in a tokenizer because it's Hugging Face's data collator with padding, again, just like the tutorial. And similar to FastAI, we can do show batch. And so here we see a decoded batch of data with our input text, as well as the label of 0 to 1. Eventually, I will probably look towards having this actually decode the values with some sort of vocabulary, but for right now, this is what the framework looks like. So we have data. We have built data loaders from raw Hugging Face datasets. All that's left is to fine tune. So here we have the sequence classification tuner, and I'm also going to import the strategy class. Now we're going to keep it at that high level enclosed API I mentioned earlier. So when we call sequence classification tuner, you'll notice that it pretty much has the same keyword arguments as fast.ai's learner, plus the addition of passing in our tokenizer and our model name. So here we can do that by just saying sequence classification tuner, data loaders, model name, the dataset's tokenizer, and then in our case, because I don't have this automatically done yet, we're going to pass in the number of classes that we expect our model to be trained for. So in our case, it's 2. Once we've built our tuner, it's going to go ahead and grab it from transformers. And as I mentioned before, we only have about 4 or 5 functions available to us right now. And the goal of that being, let's not overcome the user with too many things. And we can actually see that ourselves. So if we do, for instance, dir, which pulls up all of the attributes, and I pass in tuner, you'll see that if we go to the non-private bits, there's only a few real attributes that you're able to see. Data loaders, export, tune, some things you'll recognize from the fast.ai framework that you probably use constantly, but nothing else that you particularly don't need. So what's next? Rather than fast.ai's fit, we have the tune function instead. Now, this is a wrapper that attempts to essentially combine every single fast.ai fit function into an easy-to-use API. And this is where that strategy class comes in. So if I try and do a tab completion on strategy, you'll notice that we have cosine annealing, one cycle, and SGDR. You probably might recognize that those are the fast.ai fit functions, and that's exactly what they do. So when I call tune, I pass in the number of epochs, the learning rate, same as you do when you call fit, a fitting strategy, such as fit one cycle or fit, any callbacks that you want to add, same as you would with fast.ai's API, and then any other keyword arguments that might be needed to pass to those specific fit functions. So to train, it's just tuner.tune, 3 epochs, 5e-5, same as the tutorial, and we're going to say we want to fit with the one cycle policy. And 3 epochs later, we're at about 85% accuracy, which is roughly what you'd expect. So now we have a fully trained model, and we want to be able to use it. So we're going to first save our model away via tuner.save. And what this did is stored away essentially a Hugging Face model for us. So it's not just the weights, it's everything Hugging Face needs to rebuild your model. And there's a specific reason for that. So let's look at getting predictions. So there's 2 different ways for us to get predictions. If you're using the fast.ai framework, you're probably familiar with the .predict method. This specifically is available in the sequence classification tuner class and any of the tuner classes. So we're going to use one of the examples, which is these 2 sentences. So we're going to combine this into one string of 2 sentences, which is no different than what Hugging Face is really doing under the surface. And then if we look at the documentation for predict, we can see that it takes in both a single string and a list of strings. So it can do batch inference automatically and also has this detail level parameter. And so as you can imagine, this is pretty flexible because I can pass in any number of sentences I want and just get exactly what I need. And so if we do predict here, you'll see that we get label 0, some probabilities, and our input back. And that doesn't quite look right because we don't have label 0, label 1. We need the actual classes. And the reason for that is we use something called we use Flare underneath the surface for a lot of our bits and pieces. So for right now, I have this override little function here, or for us to essentially make a class and give it classes like it's expecting. Eventually, this will be just an API call. And now, if we do predict, we'll see that it's saying not equivalent. So that's one way to use the inference API. But what's another way? So AdaptNLP started out as an inference framework. And so it was very important to me to keep that availability there. And that is through those easy modules. So here we have easy sequence classifier. First, you construct the classifier, and then you call tag text, which wants the sentence, the model name or path. And then here I'm actually able to pass in the class name. So I'm going to say equivalent or non-equivalent. So it's going to load it. And I know it's not quite 100% right. Our model might have trained a little weird this time around. I'll have to look into that because those should be equivalent. But actually, it looks like it's just random weights. It didn't actually train. Wonder if I didn't train it beforehand, which is fine. But you'll see that, we have exactly what we got back when we called predict. And so what that means is under the hood, we're really using the easy classes. As a user, that doesn't matter. Just know that there's two separate APIs if you just want to do inference and if you want quick inference while training. The other thing you might have noticed, though, is we have this detail level parameter. What does that do? One of our customers noted that originally AdaptNLP gave you too much information. So rather than it just being like predictions, probabilities, and your original sentences, it would give back a bunch of nonsense too that usually stemmed from Flare. And so I took the choice of adding in a detail level. So here, just as a quick example, we can see a detail level low gives us what we had before, whereas a detail level of medium and high returns the same thing for sequence classification specifically, gives us our class vocabulary, the pairings of sentences to their probabilities, as well as everything else before. This is just an added little benefit and cleaner API, in my opinion, so that the user can choose what they want and don't want to return. But basically, that is the entire AdaptNLP API. Currently, it only supports sequence classification. And really, I'd recommend using this task dataset hybrid API rather than the boilerplates right now, just because it's extremely unstable. And like literally next week, I'm wrapping up sequence classification and going into token tagging. But that's it for my demo. So thank you, Wayde, for inviting me on. And I guess we'll take questions.
Thanks, Professor. There's a question. When you're returning data loaders, are you returning fastai data loaders or PyTorch data loaders?
That is an excellent question. The answer is neither. We're actually returning adaptive data loaders. Now, all that is, if it lets me pull up the source code, is a very quick wrapper around fast.ai's data loaders that stores the tokenizers and has a custom show batch. I didn't really feel a need to have everything fast.ai's data loaders have. And so I'm choosing an option of only implementing what's actually needed. And so in our case right now, that is show batch.
Awesome. Yep, there are no other questions, but I just want to point out that it also, maybe it's just my bias, but it feels like all of these frameworks are really good for also just like the top-down approach, as we call it. So that's really awesome. I don't see any other questions coming in.
Sonia, I really like how you snuck in calling Zach professor again. You know that gets to him, and I love how you just got that in there without any hesitation or anything.
I don't fight it anymore. It's not worth it.
You could be called worse things than that. So,
That's
I
fair.
that one.
You have to accept it now.
I'll at least tolerate it. Let's go with that.
All right, Arto, are you ready?
Yeah.
All right.
Let me share my screen. Let's go. Okay. Can you see my screen?
Yes.
Cool. So I will be presenting Fasthugs. It's a small wrapper library, very similar to Blur, and actually highly inspired by Blur. And it's designed to allow training Hugging Face pre-trained models with fast.ai training loop. Okay, and as you will see through my notebook, it's like really very similar to Blur in many design choices. So let's go to those. Yeah, so the main goals I had in mind when creating Fasthugs. So I wanted to have this integrated with Hugging Face datasets because they come with a lot of very useful functionality. So they rely on PyArrow tables, which allow you like not to load all the data into memory, but have the data on your hard drive and dynamically load that for training. Yeah, the datasets library is evolving quite fast, and it has a lot of cool stuff there. Now they support streaming data sets, which basically allows you not to download all the data to your hard drive. And when you deal with some huge data set, like for pre-training language model, it might be like a couple hundreds gigabytes. And with Hugging Face datasets, you can just iterate through the data, not loading everything down. And for example, in this way, you can handle large data sets with Colab, which it has some like memory restrictions, but with the streaming mode, you can do that. So I wanted to have this all the datasets functionality available. The next thing, I wanted a familiar fast.ai interface, and what I'm using Datablock API and Learner for training and callbacks for tweaking the training loop. And like my main goal was to allow for quick experimentation. So with transformers, trainer API is really great and useful. It comes with a lot of built-in support for like data parallel training, model parallel training with deep speed and all the good stuff. But like if you want to do some quick experiments, it might be a bit more difficult to use trainer because you need to basically customize a training step. And yeah, the same with writing your own training loop, right? And fast.ai allows to tweak your training loop with callbacks, and by doing that, it really facilitates like quick experiments. And that's what I wanted from this library as well. So the main components of the library are it relies on transforms for processing data. And I have a bunch of these different transforms which are applicable in different situations. And like examples are like talk transform, which will tokenize a single text, or talk batch transform, which will tokenize batch of text. And for example, you might get from your, like you can pre-process the data in data sets, and you might need only to pad your batches. And for that, we have another transform, and there is a bunch of other transforms which are specific for some other tasks than sequence classification. So you can check out that in the documentation for Fasthugs. The next thing, I'm using Datablock API to create the data pipeline, and I have some customized data blocks which uses transforms mentioned above, and put that all together to allow like quick definition of your data pipeline. And next, I'm using like a subclass of learner from fast.ai, which has some like transformer specific stuff. And most of the work is done by this callback, which handles the like putting batches of data into proper format for the Hugging Face models. And we can do a lot of stuff with callbacks as well. Like, for example, you might want to generate your predictions rather than like for autoregressive models, and you can do that with callback easily. Also, you can use like metrics from Hugging Face datasets library, and you can do that with callbacks as well. And you can probably do whatever you want with callback. Yeah. So now let's get to the notebook, actually. So I'm running this notebook on Colab, and I can post a link in the chat if you maybe would like to follow along. You can run it live and go through the notebook with me. Okay, so yeah, first what we need is to install the libraries here. Yeah, we install transformers, datasets, WNB, and TQDM. And yeah, I'm installed as well as Zach, like the library is kind of changing. And that's why you probably want to install the version from GitHub. Yeah. So let's go to the MRPC dataset. It stands for Microsoft Research Paraphrase Corpus, and it's part of the GLUE benchmark. This GLUE benchmark is one of the most widely used benchmark for measuring the performance of language models. And it essentially contains a lot of sequence classification tasks, as well as one regression task. And in particular, MRPC dataset, it contains like pairs of sentences, and your task is to output a label for this pair of sentences, whether the sentences are equivalent or not. And yeah, and the dataset is pretty small. It contains below 4,000 samples. So that's something to keep in mind when working with it. Okay, so now to the data block definition. To create data loaders, we are using here data block API. And here we have two data blocks, one for the inputs and one for labels. And the one for inputs is transformers text block. And it is initialized given a model name. And that is done to let the data block know which tokenizer to use. And this data block for labels is a slightly customized category block from fast.ai, which accepts like the label names, because fast.ai dataset already has this names for the label we have. We have two labels, and one is not equivalent, another is equivalent, and we want to use that from the dataset. Okay, and yeah, basically, if you are familiar with fast.ai, you should recognize this piece of code. We are defining this data block, providing some blocks, and also getters for X and Y. In our case, we have sentence 1 and sentence 2 for X and label for Y. And also we provide the splits, which show the data loader what data is used for validation. And we get those splits just with here with this helper function, which basically uses the names of the data sets within the dataset dict provided by, like, loaded from the datasets library. Okay, and then we construct the data loaders just as done in fast.ai and in Blur as well. You can see that this part is very similar. And we can use show batch to actually visualize our inputs. It's always a good idea to keep an eye on what are you training on. And here you can see that we have 2 sentences and a label for this sentence pair. And I will be using WNB for experiment tracking. It's really nice to have all the experiment related information stored in one place. And here we define some variables which are basically constructed here. I provide a like I will tag the run with dataset name, the task, and the model I use. And also I will group this by learner rate so that I can post-analyze all the stuff and compare different hyperparameters afterwards. And you can check this run by going to the weights and biases, and you see the training loss is decreasing nicely through the training, but the validation loss, it kind of goes down and then goes up again. So we have some overfitting here. Yeah. Okay, now let's look to the training. And the training is, again, very similar to what you do with fast.ai usually. You just get the model from Hugging Face Model Hub, and the model is defined by a name. In this case, I'm using Roberta base model, and yeah, usually it's always like unless you are doing some benchmarking, you probably don't want to use the vanilla BERT. But you would like to use some of the variations of this model which grant better performance. And yeah, it's very similar to the BERT, but like trained on more data. That's Roberta. Okay, and yeah, we define the metrics we want to use. For the MRPC, we use F1 score and accuracy to measure the performance. And then we define a learner and use FP16 to speed things up and save some memory on GPU. And you can check the training loop. Basically, this trans learner I use here, it adds this trans callback, which is responsible for basically the communication between the data loaders we have and the model. So with that, we can run the training, and we can add the weights and biases callback and save model callback. To the save model callback will store the best model we had during training by using the metrics we choose. And weights and biases callback basically logs the data to the weights and biases. And as you can see, this was used by Wayde as well. So yeah, and after the model is trained, you can call show results method to check what predictions are correct and what you see we have here some incorrect prediction. So it was supposed to be equivalent, but the model decided it's not. So yeah, it makes some mistakes. And after the model is trained, you probably want to get some predictions, and it can be done easily by constructing the test data loader from the data set we downloaded, and yeah, calling the getPreds method of the learner. Okay, and to wrap this up, I wanted to speak a bit how to improve the model performance. Like one thing you can do, you can experiment with the backbone model you use. And some popular choices are Roberta, the ones that I used. There is Albert, which uses some smart parameter sharing and shows good results on many tasks. There is Electra, which has like modified the pre-training objective and also has very competitive performance. And in this example, we will look how to use the dBERTA. It used disentangled attention, and basically this was the first model to surpass the human performance on superglue benchmark, which is kind of more difficult version of glue, which we are using here. And as you can see, like trying another model is as easy as just changing the model name here, and everything afterwards is just the same. So we can start another run with this different model and see if it performs better. And yeah, once you do that, like you probably want to get some understanding if you like utilize your model the best way you can. And for that, you can do some hyperparameter search. And this is really easy with weights and biases. So weights and biases has this sweeps functionality. And to use that, you basically need two things. You need to define a training function, and you need to state the configuration for sweep agent. You basically provide a range of hyperparameters for the sweep agent to use to start the runs. And here you can see this train function. It just wraps all the code we had before into like a single function. It will, and the sweep agent can launch this function, and basically this will do a one round of fine tuning, like here. And yeah, we can define some ranges of parameters to use for the model. And say we want to do a grid search and inspect a bunch of learning rates for our model and values for weight decay. And maybe we want to use some kind of learning rate decay with model depth. So that will, if you are familiar with fastai, you probably know that fastai often uses this differential learning rate, basically having higher learning rate for the lighter layers and lower learning rate for the deeper layers. And we can do that here. For that, you need to split the model parameters by layers into groups. And here is a function to do that. And you can basically define this learning rate decay by some factor with which the learning rate gets lower as we go deeper into the model. And yeah, there are some controversy if this really helps or not with transformers. And like some papers use that and find it helpful, other papers don't. And actually, you can just try it for yourself and see if it helps with your tasks. And luckily, the MRPC dataset is quite small, and you can run these sweeps quite fast for yourself. So here, like we define this sweep configuration. It has the project name, entity name, like a name for the sweep, a message to use for hyperparameter search and the ranges of the hyperparameters. And then you just initialize this sweep and you run the agents by running this command from bytes and biases. And it's nice, you can run multiple agents if you have like access to more than one GPU you want to use. You can launch this training runs concurrently, and the weights and biases agent will manage all this for you. Okay, and that's really nice for hyperparameter tuning. And yeah, let me briefly show you the example of what this actually outputs. So here is some sweep I ran with DiBerto model, and basically you can have a look at different hyperparameters you used, and this set of hyperparameters is linked to some performance. So here you can see that some of the best runs were with higher learning rate and zero weight decay. But you can run this for more combinations of hyperparameters, and maybe you can get even better score here. So that's a really nice way to automatically search for the best set of hyperparameters you can use. Okay, so I think with that, I'm done with my demo, and you can play with this notebook, and yeah, let's get to the questions.
I think there's just a general appreciation of the framework and also how nice it is that you can track all of this very conveniently. And for me, I was also really happy to see you for the first time. I've heard Wayde and Zach earlier, but it was really awesome to see you. I'm just scrolling through and picking the questions. So how did you learn that DiBerto was the first model to surpass human performance?
Well, that was in the paper. So they actually advertise it as one that it was first to surpass human performance on that particular benchmark. And a thing to note here, not this base model we are using here, but the largest one was the one to surpass human performance. It kind of much larger.
I don't see any other questions, but again, I think all of these presentations were really awesome. They were like very fast AIE and yet also similar and different. So that was really awesome. So thanks everyone.
Thanks for having me here, and thanks to Wayde for starting this great learning group. So,
my
hope
pleasure.
it's useful for everyone involved.
Absolutely. Like the timing was perfect because I started this rework of AdaptNLP maybe 2 months before Wayde started doing this thing. So it really made sure that I put things into gear.
Yeah, I got you motivated over there.
Something like that. Motivated, terrified. I don't know. Pick your poison.
Anyways, yeah, great demos. Thank you, Art. I think this is the first time I've talked to you as well, Arto. Correct? Like kind of in person, virtually.
Happy to meet you all as well.
Yeah, that was awesome. Anyways, okay. We're gonna wrap things up here. I talked to Andrea. I'm like, I think we might go long. And she's like, I gave you guys another 45 minutes. And I'm like, obviously she knows fast.ai folks. We typically go long. And if you've been in the course, you know, like it could go 2.5 hours, it could go 4 hours. But let's just wrap things up. So great demos. Encourage everybody to look at the documentation for each of the libraries, play around with them, and dig into them. And like Zach was mentioning, I think Arto mentioned, I mentioned, you will see the centrality of the fast.ai callback system and how important it is to the development of these libraries and other extensions to fast.ai. So for homework, watch the official course videos from week 3. Again, you're going to learn about trainer, how to do things with a raw PyTorch, training and validation loop, and also how to work with Accelerate. And as promised, we're going to have some competitions and demonstrations for you all to participate in a few weeks. And here they are. We have 3 winners per competition. You can submit to 1, 2, or all 3 of these. You can submit multiple times. And we got some swag from Weights and Biases in the form of t-shirts for you to go around and brag that you were one of the winners of the Hugging Face Fast.ai study group. And so here are the 3 competitions that we're hoping folks get involved with. One is best blog post on training transformers with Fast.ai, and just submit your links to your blogs to my email. And again, the prizes for all these, we're going to do the top 3 is our Weights and Bias t-shirts. The second competition is basically taking what you've learned and either using one of the libraries or coding your own thing and using Fast.ai to train a model on the SST2 data set. And this will be very familiar to folks. It works a lot like MRPC, except there's just one sentence. And let's see what you all come with. And also, no cheating. So use the training and validation set. If I find out you use the test set, I will send Sanyam to come over there and disconnect your Zoom. So please use a training and validation just like you normally would. We'll evaluate this and we'll announce the top 3 if we get at least 3 in a few weeks. And lastly, most interesting application of a Fast.ai trained transformer. One of the toughest things I've encountered as a software developer is just deploying something. It's hard, and everybody has a challenge with this, and especially ML folks. We know how to train models and build things in Jupyter Notebook, but can we actually deploy that so that it's useful to an end user? And so for this competition, we're looking for folks who have something, and it could be something really simple, but that shows a demonstration of how a trained transformer can be used. And hopefully you guys will be creative with that. All 3 of these are due by August 3rd, 12 p.m. Pacific time. So send me your links, send me your gist, and we'll have a demo day. And I've always wanted to say this, a big fan of watching Steve Jobs' presentations. He always had that one more thing. So I have one more thing, and that is that there will be a week 5. So next week, we're going to cover section 4. Week 5, we're actually going to do a general Q&A. So bring all your questions. And we're going to give competition winners the opportunity to present their work if they choose. We're going to provide our feedback and go from there. The Zoom link will be different. So you'll get a different Zoom link for week 5. But hopefully we'll see everybody there, and looking forward to kind of seeing what the community submits in terms of those competitions and looking at others' works. And that's it for me. Any final questions, thoughts?
I'm just looking forward to reading all of the posts and solutions that come up. I'm just here to learn. It's my greedy way of learning by being a co-host. Although I'm really not doing anything, but I'm really learning a lot. So please keep the submissions coming in, and I look forward to learning even more from them. And thanks to everyone for joining.
Yep, thank you.